Hello everyone. Let's do a couple of examples of applying the conservation of angular momentum. So in our first example, we have two disks mounted on a low friction bearing so that we don't have to worry about, any friction or anything like that, so they'll just keep spinning. And they're brought together so that they couple and rotate as one unit. So this is analogous to two carts, right, linearly, and they get stuck together afterwards, right, and move as one big thing. The first disk has a mass of 2 kilograms and a radius of 0.5 meters, and it's spinning at 450 revolutions per minute. The second disk has a mass of 4 kilograms and a radius of 0.5 meters, and is spinning at an even faster 900 revolutions per minute in the same direction as the first. So they're both rotating in the same direction. They then couple together. This is kind of what goes on in, say, like a transmission in a car or something like that. Okay, so you can imagine these two disks spinning, and then they come together and become one thing, right? They stick together. So I want to know, what is their angular speed after coupling? Well, if the system is the two disks, right, then it's an isolated closed system, and therefore angular momentum is conserved. So the initial angular momentum of the two separate disks has got to be equal to the final angular momentum of the combo disk because it's moving together. Initially, the angular momentum would be the sum of the angular momentums of disk 1 and disk 2. Finally, we could do this two ways. We could say final 1 plus final 2 and then realize that they would both have to have the same angular velocity because they're rotating together. Or we could treat them as one big disk, right, with an angular momentum, which is probably the tact we took more often when we did similar linear problems to this. Okay, so that's why I left it as just LF. Well, each of these angular momentums is rotational inertia times angular velocity. They're different, so I got to label I1 W1I plus omega 1I plus I2 omega 2I. And then over here we have the total rotational inertia times omega F. Plug in the rotational inertias. Well, be careful. This is a disk, right? They're both disks. Disks have rotational inertia of 1/2 mr squared. Now I'm going to get a little crafty here with my m's and r's. Okay? Notice that they have the same radius. So I can just call this r and r. I don't have to call it r1 and r2. Note that the masses are integer multiples. So the first disk has a mass of, I'm going to call it m, and then the second disk will have a mass I'm going to call 2m. All right, and this way we can kind of cancel some things out, right? So it's kind of a clever way of setting it up without actually working out with all sorts of subscripts and doing all the algebra and plugging the numbers in at the end. So the first disk has a rotational inertia of 1/2 mr squared. The second disk has a rotational inertia of 1/2 times 2m times r squared, because it has twice the mass. The combo has the rotational inertia that's the sum of the two. Notice that the 1/2s cancel, the m's cancel, and the r squares cancel. So lots of stuff cancels out writing it this way, which is why I like writing it this way as opposed to m1s and m2s and omega 1s and omega 2s that are going to get difficult to keep track of. So we end up with a much more simplified omega 1i equals 2 times omega 2i equals 3 times omega f. Solve for omega f, and then we just need to plug the values in, and we can find the final angular velocity, right, of the combo. So they're rotating in the same direction, so I'm going to call that a positive direction. Now, they're both in revolutions per minute, but the question didn't say they couldn't be in revolutions per minute. And so if we leave them, notice if we leave the units as revolutions per minute, we're just going to get an answer of revolutions per minute. Sure, we could convert to radians per second. There'd be 2 pi radians in a revolution, and of course 60 seconds in a minute. And we could convert these, but it didn't ask for that. If it had said what's the angular speed in radians per second, or if this was a multiple choice problem and the answers were all in radians per second, well then we would need to do it. So Add, multiply, divide, and you get 750 revolutions per minute. Now I want you to notice that that final angular velocity is much closer to the angular velocity of disk 2 initially than the angular velocity of disk 1. It didn't just split the difference, right? It didn't just add up and divide by 2. It ended up being closer to this one. Why? Well, because disk 2 had more rotational inertia by the fact that it had twice as much mass, right? And so it would dominate a bit, and so we would expect an answer that would be more than the simple average of the two. Okay? Part B. What if the second disk was spinning at 900 revolutions per minute as it was before, but this time in the opposite direction? What is the angular speed after coupling? Well, I'm not going to redo the math because the conservation of angular momentum is really all the same. So we end up in the same place. We just have to plug in a negative here because it's going in the opposite direction. If we're calling this one positive, this one would be negative. Work through, and we just, because of how all the numbers work out, we end up that it's going to change direction and end up rotating clockwise at 450 revolutions per minute. These are kind of hard to predict without actually doing the conservation of angular momentum. Right? You might be able to get an idea, but kind of hard to figure it out without running the numbers, which is why we do the physics. Here's the second little problem, which I kind of enjoy. Here we've got two twins. They must be twins because they each have the exact same mass. And they're sitting on the end of a board, which has a narrow board, which has a length L and also has a mass M. Very strange, okay? These twins have a mass, each of mass M, capital M, and so does the board. The board is pivoted at its center and is free to rotate in a horizontal circle without friction. Treat the board as a thin rod. So our axis of rotation's here, and they're going to rotate in a horizontal circle. Can you visualize this? So it's kind of like they're on a teeter-totter that doesn't teeter-totter. It spins. You used to be able to find things like this back in elementary school playgrounds. Not anymore because they'd be afraid of kids flying off and hurting themselves. Right? But it's kind of a teeter-totter that spins if you want to think about it that way. Okay? So part A, I want to know the rotational inertia of the entire thing, the board and the children, about the axis through the center of the board. Well, we obviously haven't derived this rotational inertia before, right? But couldn't we break this up into three pieces? This kid, and the board. So we could then say that the total rotational inertia is the sum of the rotational inertia of the board plus 2 times the rotational inertia of the child. Now, the reason I'm doing it this way instead of child 1 and child 2 or child right and child left or something like that is because they're going to have the same rotational inertia because they're the same mass and they're the same distance away from the axis of rotation. So even if we treat them as particles, their mr squareds would be the same. So the distance from the axis of rotation to either child we will call L over 2. We do know the rotational inertia of a thin rod about an axis through its center. We derived that one in class. It is 1/12 ml squared. And the two children would be 2 times m times the quantity L over 2 squared. Right? This is really mr squared for each kid times 2 because there's 2 of them. All right? So if we do a little math, we end up with 1/12 ml squared plus 1/2 ml squared. Well, that would be 6/12 plus 1/12. So the total rotational inertia is 7/12 ml squared. Now, it's not really as hard as it looks. It is a nice problem in that all the masses are the same and the kids are the same distance away and everything. So this problem could get much harder to do, right? If the masses were different, if the kids were at different distances from the ends. I mean, lots of variables you'd have to keep track of that. But in this case, we can do some tricky little things here to figure out the rotational inertia totally. Part B, what is the magnitude and direction of the angular momentum of the system if it is rotating with angular speed omega sub O in a clockwise direction, as seen from above? Well, first of all, the angular momentum of this essentially rigid object rotating about a fixed axis would just be I omega. Right? And the I would be the I we just found, 7/12 ml squared. And the omega would just be omega sub O. So here's the angular momentum of the entire system. Now, in terms of a direction, right? So if you're thinking clockwise, rotate your fingers of your right hand in the clockwise direction, right? And what direction is your thumb pointing? It's pointing down, right? It's pointing down. So this has a downward angular momentum. I know that's weird, right? You got to think of this. Remember, it's rotating in the horizontal plane. Right? So rotate your fingers in the clockwise direction. Thumb points down. So that one was pretty easy. Here comes the fun part. So while it's rotating, okay, while it's spinning at omega sub O, the kids kind of grab on and shimmy their way up so that they're now half as far away as they were before. Okay? You with me? So they go from outside to halfway in. The first thing I want to know is, what is the ratio, means put it in a fraction, right, of the new rotational inertia to the initial rotational inertia, which we already calculated as 7/12 ml squared. Well, now each kid, so that's the initial rotational inertia. Now each kid is how far away from the axis of rotation? Well, they're L over 4 away, right? Half of a half. So the final rotational inertia will be the rotational inertia of the board around an axis through its center, 1/12 ml squared, plus each kid, so 2 times, their mass times their distance squared, L over 4 squared. Work out the fractions and everything, and you get 5/24 ml squared. Put this in the ratio of new to initial. The new would be the final, right? So final to initial, and simplify. Some of you on a previous test, what was it, the energy test, I think, maybe, were asked to put some kinetic energies in a ratio, right? And you didn't simplify. That is sloppy. You may lose a point on an AP test if you don't simplify. So we end up with 5/24 over 7/12, which, if we work the fractions, is about 5/14. So notice that means the final is smaller than the initial. It's only 5/14 of the initial. Does it make sense that the final rotational inertia got smaller? Well, I hope so, because the kids got closer to the axis of rotation. Right? That means the mass is closer, and if the mass is closer, should have less rotational inertia. So you should have been looking for a ratio here of less than 1, which indeed we got, right? It's about 5/14. Part D, what's the resulting angular speed in terms of omega sub O? So how fast do they end up spinning? Okay, so first off, again, if the system is all of them, and since it's frictionless, right, it's closed and isolated, and therefore angular momentum should be conserved. So the angular momentum that they have when they're sitting on the outside must be equal to the angular momentum they have sitting here. Each angular momentum is going to be a rotational inertia times the angular velocity. So the initial angular momentum is the initial rotational inertia times the initial angular velocity, which we already called omega sub O. The final is the final rotational inertia times the final angular velocity, which is what we're trying to find. Solve. We get the ratio of the initial to the final rotational inertias times omega sub O. Well, we could plug these in, but don't we already know this ratio? Be careful. We know the inverse of that ratio, right? IF over II is 5/14. So that means II over IF would be 14/5. Note that means they speed up. Well, I hope that makes sense, right? The rotational inertia decreases, so the angular velocity must increase, proportionally speaking, in order to keep the total angular momentum conserved. You almost could have predicted this once we did part C, right, and got the ratio of the rotational inertias. Now, for reasons which will become apparent in a moment, I want to know what the change in kinetic energy of the system is. Right? Change in kinetic energy. So, total kinetic energy or change in kinetic energy is going to be final minus initial. Well, these are purely rotating things here, right? So we use the rotational version of the kinetic energy, 1/2 I omega squared, right? Final minus initial. We already know the rotational inertias, right, in terms of basic quantities. The final was 5/24 ml squared. The initial was 7/12 ml squared. Right? We also need to, since we're going to find the change in kinetic energy, we're going to plug in our initial angular velocity as omega sub O, and our final angular velocity, as we found in the previous part, is 14/5 omega sub O. You see all the substitutes we made? This is so that we can compare the kinetic energies in terms of our initial quantities. Right? So lots of substitutes. Now, tons of fractions. Have fun with the fractions. When you're done, you should get 21/40 ml squared omega sub O squared. Now notice something though. This is a positive change in kinetic energy. So that means that kinetic energy increased by this much. Well, wait a minute. This is an isolated system, right? So there's no work being done here. How can the kinetic energy be increased? There's no springs. They're not changing heights. So there's no other energy storage mechanisms here that could end up being the EK. Or is there? Do you see it? Do you see where the extra energy comes from? It comes from the kids, right? They have to do work on the system by pulling themselves forward, right? They're not just going to be able to slide forward, right? They're going to have to grab on the board and yank themselves forward as they go. Right? And even though that's internal, right? That's internal. Technically, their stored energy in their body would be less. I mean, think about it. If it was you, right, it might make you tired to slide yourself around on there. Okay? So the added energy comes from the work they do in pulling themselves forward, not from some outside source, right? Because it's an isolated system. Oh, one thing to add here. Note, the angular momentum stayed constant, but the kinetic energy increased. Isn't that interesting? Right? So the kinetic energy wasn't conserved, just the angular momentum was. Right? The kinetic energy increased. Now, you might be wondering, though, why is that? Right? Because we showed earlier that the angular velocity increased by the inverse ratio of the rotational inertias. Right? The rotational inertias got smaller by 5/14, but the angular velocity got bigger by 14/5 in order to keep the angular momentum conserved. But why would the kinetic energy increase then? I mean, I and omega change in proportional ways. I'll be careful. Omega is squared. So a change in omega dominates over a proportional change in rotational inertia. Right? So the rotational inertia goes up by, decreases by 5/14 when they pull themselves in. The rotational inertia goes up by 14/5, but that gets squared. Right? So it doesn't end up canceling out. You with me? It ends up increasing the kinetic energy. Kind of an interesting little problem. Hope you enjoyed solving some problems of conservation of angular momentum.